Hello everyone. Today we're going to talk about wavelets. The prerequisites are linear algebra, in particular basis, projections, orthogonal complement, direct sum, Fourier series, discrete Fourier transform, and short-time Fourier transform. Okay, so in order to motivate why wavelets are useful, let's take a look at an image. And let's notice that in some parts of the image, the features of interest have very large scale. What do we mean by that? If I look at this part here, it's essentially constant. So one would say that there's a feature here that essentially has around that scale. Again, these concepts are tricky, and we will see that defining them mathematically is not completely trivial, but intuitively, the changes in the image around here are very coarse. Like there's not that much change as we move around. Whereas here, the changes are much finer. And if you go here, the changes are really, really fine. So here we have a lot of information at very fine scale. Here at, less like coarser scale. And here at a very coarse scale. This becomes even clearer if we take a line within the image. And we take a look at the intensity values of the pixels along that line. So just to be clear, this is a line that I don't remember, but I think it's around here or something like that. What you see is there's an area where things are constant, so not much is going on. So one would say that the features there are at a very coarse resolution, whereas in other parts, especially here or here, a lot is going on. Over finer scales. Okay, so now the idea is to find some kind of analysis that allows us to understand or analyze at what scales and resolutions the information is encoded in different parts of the image. The motivation is that the resolution at which information is encoded is usually not uniform. There are parts where information is basically encoded at a very coarse scale, so not much is going on as we move from pixel to pixel here, whereas in other parts, information is encoded at a much higher resolution, at much finer scale. Okay, and what we want to do is to decompose signals into components that have different resolutions or different scales in order to perform this analysis. And the challenge is that we want to design a basis of vectors that is able to achieve this. So if you think of the Fourier series or the discrete Fourier transform, the Fourier series and the Fourier transform use basis functions that essentially look like sinusoids, so they look like that. So they are, first of all, not localized in space, so we're not going to be able to make a difference between different parts of the image or the signal that we're interested in. And second of all, there is a bit of a concept of scale in the sense that higher resolutions capture finer scales, so there is that. But the problem is that we're not localized in time. The short-time Fourier transform essentially cuts up a signal into segments, so that actually gives you some space localization. But these segments are all of the same length. So we would have something like this. This is closer to what we want. This is what the Fourier transform, like the short-time Fourier transform, gives you. But these segments all have the same length. This is not going to help us very much if we want to capture information at very different resolutions and scales. Okay, so in fact, you can get wavelets by just taking the short-time Fourier transform and employing segments of different lengths. But today we're going to take a different route to define wavelets, which is simpler. Okay, so the idea here is that we want to design bases of vectors that are able to extract information at different resolutions or different scales. If the vectors are orthogonal, then it's going to be much easier to project onto different scales or different resolutions. And that's what we're going to focus on today. There are some reasons why you wouldn't necessarily want these vectors to be orthogonal depending on your application, but today, for simplicity, we're going to focus on orthogonal wavelets. The way we're going to go about this is we're going to start with a very concrete example, just so that you get a little bit like the visual intuition about what is going on when you do wavelet analysis. And then we're going to take a step back and try to formulate a mathematical framework that corresponds to this analysis, okay? But first, let's go through an example to make sure that we get the intuition. So we're going to use a low-pass vector called the scaling vector of Father wavelet to extract the coarsest scale. Okay, and this is going to be achieved by just taking an inner product with a constant vector. This is just going to give us the mean of the signal, and that's what we're going to call the coarsest scale or the coarsest resolution. So let's go back to this signal that we have here, which, remember, corresponds to a line within this image of New York that I showed you before. And now we're going to do a very, very coarse approximation of this, where we say, okay, we're going to approximate this by just a constant function, you know, like a constant, a scaled version of this constant vector, and that's going to give us what the information the signal contains at that very, very coarse resolution. Okay, so here what I'm showing is this approximation, which is just a constant. This is the best constant approximation to the signal that we find by projecting onto a constant vector. And this is the coefficient. Okay, this is not super interesting. We probably want to go to finer resolutions in order to understand better what the structure of the signal is. And to do that, we define mother wavelets. So the father wavelet intuitively takes care of the coarsest resolution, the lowest resolution information that there is. And then now the mother wavelets allow us to extract information that is at finer and finer resolutions, okay, at different resolutions or scales. And we do this by taking inner products with shifts and dilations of a certain vector called a mother wavelet. If we can choose the shifts and the dilations so that the basis vectors are all orthogonal, then our life will be much easier. And in fact, we can by designing it like this. So this is going to be our mother wavelet that is going to extract information at different resolutions. See that it's basically just a jump from -1 to 1. We're going to shift it in a way that it remains orthogonal. So here, just to be clear, what I'm saying is like the first one looks like this, the second one looks like this. Okay, these are all shifts of the same mother wavelet, and you can see that these two guys are orthogonal because their supports are disjoint. Okay, so we take all those shifts, and that will give us information at a very fine resolution. But we also want information at coarser resolutions, and for that we dilate. Okay, so this is a dilated version of this guy. And now we also include some shifts of this dilated version. Okay, this is a shift, and these two are again orthogonal because their supports are disjoint. They are non-zero at different places. Also realize that this guy and this guy are orthogonal, and that's kind of easy to see. Because if we put them on top of each other, so just to be clear, I'm talking about a vector that looks like this, and then a vector that looks like this. When we take the inner product, because this is -1 and this is +1 and this is -1, -1, the inner product of this two guys is just going to be -1 times -1, which is 1, plus +1 times -1, which is -1, and then the rest is going to be 0 because this guy is 0 here. So this is just going to be 0. Okay, so this shows that this guy and this guy are indeed orthogonal, and you can show the same for all the others. And finally, we continue dilating, okay, to get even coarser and coarser scales. It's exactly the same idea. So now we have built a family of vectors that are all orthogonal. Oh, and by the way, all of these guys, you can check in the same way I just did, are orthogonal to the father wavelet that we already talked about. So now we can try to decompose this signal using the father wavelet and coarse versions of the mother wavelet, and then make the mother wavelets finer and finer. And that's what I'm going to do now. Let's approximate the signal using the father wavelet and the coarsest possible mother wavelet, which is basically, it looks exactly like that, right? Like it's constant over here. Okay, this is what the very coarse mother wavelet is going to look like. And then it's going to be constant over here. So we're approximating the signal by a signal that is constant over here and constant over here. That's exactly what we're doing, and you can see that approximation there. And this is the coefficient corresponding to the coarsest mother wavelet. Okay. Now we can make this approximation finer by incorporating a finer scale mother wavelet that is constant here and here, and then a shift. So basically this is going to be two mother wavelets, just to be clear. Okay, we have incorporated two basis functions, one that is constant here. Oops, actually I've been drawing it, I think, the other way around, right? Because we have, wait, just to make sure. Yeah. So these guys should be facing down and these guys should be facing up, but it doesn't really matter. Okay. So here we are incorporating a mother wavelet that looks like this and like this. And it's just equal to zeros. It's that coefficient. And another mother wavelet, I'll draw it in another color, that is 0 over here, and then looks basically like this. And it's this coefficient. And here we can see that in this right part of the image, more is going on at that scale, which corresponds visually, right? Here, essentially, once we have that constant approximation, nothing much is going on. When we use even a finer mother wavelet, we start seeing more structure here, so clearly, and especially here, so clearly more stuff is going on here. Again, here on the left, not much is going on. And we can make the approximation even finer and finer and finer. And again, we keep seeing that on the right part, there's just a lot going on, and in particular there in the middle. Okay, here is where clearly there's more change, okay, which corresponds to here. And eventually, if we incorporate enough mother wavelets, we can approximate the signal exactly. And now if we go back and we look at these coefficients essentially tell us what is going on in the signal at different scales. So in particular, we realize that on the left part of the signal, not much is going on, okay? Once we have this guy, we are essentially done, okay? Like then all the interesting things are happening on the right part and in particular in the middle. Okay, so I hope this example has given you a bit of an intuition about what a wavelet decomposition does. It decomposes the image into components that have different scales or different resolutions. Now we're going to take a step back and try to, we're going to introduce a mathematical framework that allows us to think about these things in a formal way. Okay, so we're going to assume, just for simplicity, that the length of the signal is 2 to the k. And now this multi-resolution decomposition, we're going to think of it as a sequence of nested subspaces. Okay, so these subspaces are inside of each other. This is the subspace that captures the finest resolution, and the resolution is decreasing in this direction. Okay, the idea is that the subspace with the finest resolution is actually the whole, like it captures all of the information. It's Rn. Okay, so every vector is going to be in there. And then as we decrease the resolution, or we increase the scale, however you want to think about it, what happens is that these guys capture information at coarser resolutions, at larger scales. I hope I said that well a minute ago. I always get confused with higher resolution, lower resolution, coarser scale. What I mean is this is very fine scale, high resolution. It has all the possible information, and then the information, like the resolution, is decreasing in that direction. So each of these subspaces is going to be translation invariant in the sense that if we have a vector that is in the subspace and then we shift it by a shift that is within the resolution of the subspace, then the vector is going to stay in the subspace. This is going to become much clearer in a moment where I show you an example. Okay, but the idea is that, like, if the subspace has a certain scale, if we shift by that scale, you remain in the subspace. Of course, if you shift by a smaller scale, you might not remain in the subspace. And then the idea, which is why I'm saying that the resolution is decreasing in this direction, is that if you have a vector that belongs to this subspace Vj, so which is there in the middle, if you dilate it by 2, in fact, I should have said, dilating x by 2. If you dilate by 2, then you end up in this larger, coarser resolution subspace. Again, this is going to become much clearer in a moment when I give you an example. So let's actually go to the example. The simplest possible example for this multi-resolution decomposition are vectors that are constant on segments of length 2 to the k. Okay, so let's work this through. We're going to see that it satisfies the conditions. So V0 is just vectors that are constant on segments of length 1, which is very silly, right? Because any vector, arbitrary vector in Rn, is constant on intervals of length 1 because the interval is just each entry. Okay, so that's just silly. Of course, V0 is any possible vector. Now, let's think of a vector that is constant in intervals of length 4. Now, if we shift this vector by 4, okay, so like 2 to the k, so Vk contains vectors that are a constant on lengths of length 4. Now we shift it by 4. We shift this by 4. Basically what we're going to get is a new signal. Imagine that it's 0 here to the left, just for simplicity. We're going to get a new signal that is going to look like this. Like this. Let's not care too much about border effects. You can deal with them in different ways, but they're not too important. And this signal is clearly still constant on intervals of length 4. Okay, so it stays in that subspace. Now, let's think about the third property, which is that if we have a vector that is in Vj, if we dilate it, then we end up with a vector in Vj plus 1. So let's think of just a vector that is in V0. Okay, so it's constant on intervals of length 1, which is a bit silly again because it's just any vector. Now we dilate it. When we dilate it, this happens by 2. It becomes a vector. So this is in V0. When we dilate it, it indeed becomes a vector in V1 because it's constant on intervals of length 2 to the 1, which is 2. Then, let's indicate by a different color that we're dilating. So we dilate times 2. Now we dilate against times 2, and what happens? We end up with a vector that is constant on intervals of length 4. Right? When we dilate by 2 again, which exactly corresponds to the subspace V2, and so on and so forth. So these piecewise constant vectors indeed satisfy these conditions of the multi-resolution decomposition. Okay, so we can see that they are actually spanned by shifts and dilations of a Haar father wavelet, because if we have a signal that is constant, for example, in intervals of length 4, then we can just build it in terms of shifts of father wavelets of length 4, okay, multiplied by different values. So obviously any piecewise constant function we can build using these father wavelets that are essentially just equal to 1 on a certain interval. The problem is that if we just, you could think, okay, so perfect, so we're done here. We can just use these basis functions of father wavelets, and that's it. Like that, we're going to extract the information from the signals. The problem with that is that these guys are really not orthogonal. Okay, so that's the problem. These guys are not orthogonal at all. So if we use this basis vector for a coarse scale, and then we use this basis vector and this basis vector for a finer scale, the problem is that this guy and this guy are really not orthogonal at all, which means that they're going to extract overlapping information from the signal. You're not going to be able to decompose the signal into components that when you add them up together, they make the signal again, because these basis functions are not orthogonal at all. So because of that, you would like to obtain functions that are indeed orthogonal. And there's a very beautiful mathematical framework for doing this, which essentially is based on the following idea. You say, okay, so how about, because I know that VK includes the subspace with coarser resolution, which means that this subspace here, okay, that is of finer resolution, includes this guy. How about I separate this coarser resolution subspace into the subspace that includes this guy and whatever is orthogonal to it. So I'm going to separate this into like every subspace of resolution 2 to the k. I'm going to separate it into a subspace of resolution 2 to the k plus 1 plus whatever is not in that coarse resolution. So this is a very, this is something to really think about, and you'll have to work through it in the homework a little bit to really understand it, but that's the idea. The idea is that we extract the orthogonal complement at each resolution that is not in coarser resolutions, so that it captures that information which would not also be included in the coarser resolution, in the coarser scales. So let's think about it here just slowly. So here, this guy includes, vectors that have whatever, like arbitrary, that are arbitrary because they are constant on intervals of length 1. So we're going to divide this into the vectors that are constant on intervals of length 2. And for that, we have the basis functions, which could be, father wavelets, okay? But anyways, we're going to divide that into vectors that are constant intervals of length 2, and then we're going to ask ourselves, what are the vectors that are orthogonal to these guys? And what are those? Well, basically, you want something that is orthogonal to anything that is constant on intervals of length 2. You end up essentially with these mother wavelets that look like this. So maybe I'll use another color. So the idea of the mother wavelets is precisely that they are orthogonal to the coarser resolutions. So if you use mother wavelets like this, okay, you're going to be able to span a subspace that is orthogonal to every vector that is piecewise constant on segments of length 2. And now the beautiful thing is that you can iterate on this. So now we have divided V0 into vectors that are constant on length on segments of length 2 and any vector that is orthogonal to that we're going to keep. And now we're going to separate this guy into vectors that are constant on segments of length 4 and vectors that are orthogonal to those. So these guys are going to be vectors that are constant on intervals of length 4 and so on. And now W2, so I'm going to draw maybe here, is going to contain vectors that are orthogonal to these guys but are still constant because they're still in V1, so they're still constant on segments of length 2. So they're going to be essentially spanned by this dilated mother wavelet that is constant on segments of length 2 but is orthogonal to any vector like that. And then we're going to repeat by again decomposing the vectors that are constant on length 4 on segments of length 4 into vectors that are constant on segments of length 8 and again mother wavelets that are orthogonal to those. So basically we end up with a decomposition where we have the coarser scale, which would be spanned by a father wavelet, which is vectors constant on a certain on intervals of a certain length, and then we have these orthogonal complements that are all spanned by mother wavelets that are dilated and shifted copies of each other. Okay, so to be clear, if we take this decomposition down to, let's say, V3, we have vectors that are constant on segments of length 8. Then we have vectors that are constant on segments of length 4 but are orthogonal to this guy. Okay, that's W3. Then we have vectors that are constant on segments of length 2 but are orthogonal to this guy and to this guy. That's W2. And then we have vectors that are orthogonal, constant on segments of just length 1, but are orthogonal to this, and to this. So like that, we have managed to build a hierarchy of bases of these subspaces that are orthogonal complements to each other, so that in the end, we managed to decompose the signal using orthogonal vectors at different scales. And now we can project on different subspaces like this to, we can project on V3, we can project on W3 or W3 plus V3, which at the end of the day is V2, to obtain approximations at different scales. And that's exactly what we had done in the example that I showed you at the beginning, okay, when we were projecting this slice of the image. We started by just projecting on V9, which is spanned by this father wavelet, which has length 2 to the 9. Then we projected on V8 by projecting onto the father wavelet and also onto this basis for W9 that contains mother wavelets that look like that. Well, actually, I did the same mistake again, like that, the way we have defined it. Okay? It doesn't matter whether the first part is positive or the second one is positive. And this is the coefficient for the mother wavelet corresponding to that subspace W9. Now we incorporate W8, so these are the coefficients for W8, and this is the projection onto V7 that includes V9, W9, and W8. All of those make V7. Okay, just to be clear, this is V9 plus W9 plus W8. Okay, and that's how we incorporate more and more coefficients to project onto these subspaces that have finer and finer scale, and eventually we end up covering the whole space when we reach the finest resolution. Okay, so again, this would be the coefficients for W1, which are just wavelets, mother wavelets, that just look like this. Okay, and that's the really beautiful mathematical framework built by Mallat and Meyer to describe and manipulate multi-resolution decompositions. Now I want you to think, well, I want to connect a little bit back to what we're doing with the short-time Fourier transform. We could look at the Haar Mather wavelets in the frequency domain, and what we're going to realize is that when the Mather wavelets are wider, as we had learned when we were talking about windowing, their Fourier transform is going to be narrower, which means that they're more low pass. So you can also think of wavelets as filters that have different bandwidths, but they also have different time supports. And that's the main difference with the short-time Fourier transform. So in the short-time Fourier transform, we're cutting up the signal. So we have a signal like this. We're cutting up in segments with the same length. And then within those segments, we were actually looking at different frequencies. So in a way, we were looking at different resolutions or scales, as I said before, but for fixed segments, okay? Now, when we look at wavelets, we're actually cutting up time in different resolutions. So this would be for a coarse resolution, this would be for a finer resolution or higher resolution, and so on and so forth, which is what is indicated here. And then those guys are going to have different bandwidths because of that. So the wavelets that have a lot of how do you say, like a lot of like time, that are wider in time, are going to be shorter in frequency, and then the ones that are shorter in time are going to be a bit wider in frequency and reach higher frequency. So this is what we're seeing here. But of course you can see that for the Haar wavelet, the picture is not as clean as this, okay? There's a lot of overlap here. The reason is that the Haar wavelet uses piecewise constant, has a piecewise constant structure, which, as we had seen, produces a lot of artifacts in frequency. So you see all of those artifacts here. You can actually design smoother wavelets so that they look a little bit more like this picture, where they tile the time frequency, this time frequency plane in a cleaner way. But the idea is that, like with wavelets, you get things of what you get basis functions that have different time resolutions and also different frequency resolutions, and it's just a different trade-off than what you get with the short-time Fourier transform. Okay, this is just to give you a little bit of an intuition about what happens if you think of wavelets also in the frequency domain. So I started talking about images. We're not going to go very deeply into this because it gets a little bit complicated, but the ideas are actually very similar when you want to apply wavelets to images. We have focused up to now on 1D basis vectors. Just like in the Fourier transform, you can get a 2D basis vector by just computing an outer product of a 1D basis vector. So the idea would be, like, imagine just a very simple Mather wavelet that is -1 and 1. You take the inner product with itself, another Mather wavelet, okay, and what you end up with is 1 minus 1 minus 1 1. Okay, so you get a 2D Mather wavelet that looks like this. So by doing inner products between different Mather wavelets and father wavelets, you end up with 2D wavelets that look like this. Okay, so this one, for example, is clearly the outer product of father wavelets, which are just constant. This is clearly a father wavelet in one direction and a Mather wavelet in other directions, and then we see the same thing for the increasing resolutions here, or decreasing the scale. Here we see inner products between Mather wavelets and Mather wavelets. Here we also see that, but at a finer resolution. Sorry, at a coarser resolution. As you can see, I always get confused by this stuff. But that's the basic idea, okay? We take just outer products, and you have to choose what outer products you take so that the wavelets remain orthogonal. There are other ways of building 2D wavelets 2D wavelets or wavelets in multiple dimensions that are more sophisticated. I cannot be written as separable. By separable here, we just mean that separable 2D wavelets can be written as the outer product of 1D wavelets. There are other designs that are non-separable and have some better characteristics in terms of the artifacts they produce when you represent images with them and so on. I really encourage you to look into them. The steerable pyramid in particular was developed by Eric Simoncelli, who is at CDS and at the Center for Neuroscience in NYU. But anyways, the 2D Haar wavelet basis vectors look like this, and we're going to look at what happens when we decompose an image into these Haar wavelets. The approximation at the beginning is just using this first basis vector, which is just constant. So the approximation is just constant. And then we start using wavelets that are piecewise constant in this way. And this is not too interesting. When we go to higher resolutions, things start to get interesting. Realize that because of the fact that we're now in 2D and we can choose how to take these outer products, we're going to have filters that are more vertical. By filters, I mean wavelets that are more vertical, wavelets that are more horizontal, and wavelets that capture more diagonal structure. And that's what we're showing here. So we are going to see this very soon. These ones capture more horizontal structure, and these capture more vertical structure. So this is basically telling us that a lot is going on in this direction here, whereas if we look at vertical changes, they're happening here, which is where we have the Empire State Building. Again, that's what we see here also. Here and here is where the stuff is going on at this resolution. And when we go to coarser and coarser resolutions, we see that, basically you see where the vertical and horizontal structure is at different resolutions captured by these coefficients. There's much less structure here at diagonal resolutions because we're looking at buildings that have mostly horizontal and vertical lines. So here you see very clearly where the information is vertically and horizontally. There seems to be more structure vertically than horizontally, which makes sense, right? Because you see all of these lines going up. On the other hand, this horizontal structure kind of shows you this part here. And this is how you can use 2D Haar wavelet, 2D Haar wavelet decomposition to decompose signals into different scales and different resolutions. So what we have learned here is a framework for multi-resolution analysis based on wavelets. We have gone into a detailed description of an implementation based on Haar wavelets, and we have shown how to extend it to 2 dimensions. Thank you very much.